Estamos ao vivo.
Ok. Olá, pessoal. Boa noite. Sejam todos muito bem-vindos. Nós teremos hoje a nossa primeira palestra internacional do programa de pós-graduação em Química, né, que foi um convite feito pelo professor Bernardo e gentilmente aceita pelo professor Teodoro Kaufman, né, da Argentina. Então, antes de passar a palavra para o professor Bernardo, que vai fazer a introdução do professor Teodoro Kaufman, né, à nossa audiência, eu farei uma breve introdução do professor Bernardo, que é professor, né, orientador do programa de pós-graduação em Química. Então, o professor Bernardo, ele é formado em Química Licenciatura pela Universidade Federal de Santa Maria, né, instituição em que ele tem, mesma instituição a qual ele tem o mestrado, né, na área de Química Inorgânica. O doutorado ele fez pela Universidade de São Paulo, né, e ele tem atuação atualmente nas áreas, né, de caracterização espectroscópicas, espectroanalíticas, espectroeletroquímicas e de porfirinas, química de coordenação e síntese e aplicação de derivados porfirínicos contendo ligantes heteronucleares, bioinspirados contendo complexos platina 2, paládio 2 e rutênio 2. O professor Bernardo atualmente é professor da Universidade Federal de Santa Maria e é orientador no programa de pós-graduação em Química. O professor Bernardo também é bolsista de produtividade do CNPq nível 2. Então, Bernardo, muito obrigado pela sugestão, né, de apresentador para esse nosso webinário, né, do professor Kaufman, e agora eu passo a palavra para ti fazer a apresentação do nosso apresentador.
Perfeito, César, muito obrigado pelas palavras. Então, boa tarde a todos, né, por mais um webinar agora do nosso programa. Então, eu tenho o prazer de convidar o professor Teodoro Kaufman, né. Então, o professor Teodoro Kaufman tem a formação em farmácia, doutor em Química pela Universidade de Rosario. Ele é professor titular do Departamento de Química Orgânica, certo? Ele tem a formação no grupo em pesquisas de química de heterociclos, com interesses biológicos, certo? Já dirigiu de mais de 15 teses, é coautor de mais de 100 publicações, capítulos de livros, patentes, né, editor de livros também. É membro do comitê editorial de várias revistas, certo? Inclusive do JBCS, né, essa revista. Professor titular do Instituto de Química de Rosario desde 2012. E hoje nós vamos ter o prazer, então, de a palestra do professor Teodoro Kaufman, né, intitulada como Total Synthesis of Some Unique Heterocycles, Nature Products and Related Compounds, né? Professor Teodoro, the stage is yours. Thank you very much for the acceptation.
Okay. Thank you very much, Professor Bernardo. I will share with you my screen. I have an indicator here telling me that the connection is unstable. So I will try to do my best, but hope internet does its best too. So let me just share my screen. And hope you are able to see my first slide. Am I right?
Yes, this is perfect, Professor.
Okay. Thank you very much. Well, first of all, good evening to everybody, and thanks again to Professor Bernardo for the invitation. My presentation today is entitled Total Synthesis of Some Unique Heterocyclic Natural Products and Related Compounds, and I'm very pleased to be presenting this to you. This intends to be a sampler of some syntheses we have been carrying at our lab in Rosario, in Argentina, where we devote our time of investigation, of research, to the synthesis of heterocyclic natural products containing nitrogen. So it's nitrogen heterocycles and oxygen heterocycles. We also synthesize their analogs, and from time to time, we also study the biological activity of the compounds we prepare. So To introduce the subject, I will talk about the interest and the necessity of natural product synthesis in modern chemistry. The total synthesis of natural products, as well as their analogs and derivatives, is still necessary for many reasons. One of them is because it still supports structure assignment. Despite the huge progress made by computational chemistry, the last word in terms of structural assignment is synthesis. So it helps to correct misassignments. It also provides convenient routes to analogs which cannot be accessed by natural means, and provides inspiration and access to new materials for testing and for further research. It also provides a more intimate chemical knowledge of natural products, of the chemistry of the natural products and their analogs, and it is required for SAR studies, SAR meaning structure-activity relationships, to improve knowledge required to optimize activity. The synthesis of natural products is also the driving force behind the development of new reagents and reactions, and it also contributes to keep the rhythm of growth of the pharmacological arsenal, so the humankind keeps having modern medicines. And finally, it promotes progress of science through disciplinary advances and innovation. And last but not least, in words of Professor Robert Woodward, the Nobel Prize in Chemistry in the 60s, the synthesis of natural products is an intellectual challenge of such magnitude that it turns people into better persons. The synthesis of natural products moderates and modulates character, and it also builds resilience. There are so many failures when you do synthesis of natural products that you became resilient. So I will talk about the synthesis of 4 different targets, and will start my talk with the synthesis of the proposed structure of aspergillitine isolated from Aspergillus versicolor. The aspergillus is in the back of this picture, and the structure of aspergillitine in the front. So the story goes as that. Professor Lin, working in China with his group, was able to isolate a strain of Aspergillus versicolor from a marine spongia of the genus Sexospongia. Actually, it was a Sexospongia exigua. But the compound he isolated was an alkaloid. It contained nitrogen, and he made the structural elucidation using spectroscopic data. And aspergillitine was not alone. It was accompanied by 6 compounds structurally related, which were named the aspergions A to F. All these compounds share a common feature. They are 2,3-dimethyl-chromanones. And this motif is very rare, highly unusual among natural products. And I brought to you an example, one of the few available examples of natural products having this motif. This compound, compound 3, was isolated from the microbiome of the lichen Graphis scripta. And there are only a handful of compounds like this one. So in order to publish and to finish this work, Professor Lin partnered with Peter Proksch, a very known, highly recognized natural product chemist from Germany, and both groups published this paper in 2003 in Journal of Natural Products with the structures and their elucidation of aspergillitine and the aspergillones. And well, by that time, Professor Proch was lecturing, and one of his lectures and also a paper in one of the in a journal, he proposed that Aspergillus versicolor produces 2,3-dimethylchromones because it has a novel metabolism. So Professor Proch proposed that there are new enzymes previously unknown in this species which can be able to prepare to lead to 2,3-dimethylchromones. So against this background, we decided to synthesize aspergillitine. In my laboratory, as in many others, where synthetic chemistry is done, retrosynthetic analysis, this is the legacy of Elias Corey, is done previous to any synthesis. So we devised a strategy which we call strategy A, by which we disconnected this C ring and unveiled this compound 4 as a potential advanced key intermediate, because we thought that through a Friedel-Crafts acylation we could install this 3-carbon atom side chain, and using a Kostanecki-Robinson cyclization we could form this heterocyclic ring with the aid of this phenol. So next, we also disconnected the other heterocyclic ring, and we discovered that this compound 5 would be a suitable precursor of 4. This is a salicylaldehyde derivative with a substituent at this position, which can be an halogen or an OH, a phenol. So we thought that using this X group in a suitable form would help us installing the 3-carbon atom, this side chain, and we can add the nitrogen required for the heterocycle through an oxidation of the aldehyde, and actually cyclize, form the ring, employing an Asa-Heck reaction or a 6-pi electrocyclization reaction. Once we reached 5, we noticed that these kind of compounds are known, but they are non-commercial, and their access is rather laborious. So we tried to find a better way and devised strategy B. First, we disconnected the nitrogen heterocyclic ring and found that the same set of reactions could be employed if we start from this precursor 6, where X is also an halogen or a suitable protective phenol. And we also demolished this structure to find simpler compounds, and we disconnected this carbon-carbon bond, thinking that at that formulation from this compound 7, which we unveiled, could be put in place the formyl moiety, and also a Kostanecki-Robinson reaction, as before, would make the needed C ring of aspergillitine. We also found that when X is an OH, the compound is available commercially, but if X is an halogen, we thought we could synthesize the compound through a Fries rearrangement or a Friedel-Crafts acylation. So there were very good alternatives to access compound 7. So we started with compound 7A, which has an OH here, and submitted it to reaction first with acetic anhydride and sodium acetate to make an acylation of both OH groups. Then with triethylamine, under reflux conditions, we performed a Baker-Venkataraman rearrangement, which was needed to perform the third, last step, which is the which is the cyclization, leading to a full Kostanecki-Robinson synthesis of compound A in 56% overall yield. Then we performed a DAF formulation with hexamethylene-tetramine and acetic acid, to which a small amount of water was added. This is the Rishnovsky modification of the DAF formulation. And after heating this for 2.5 hours at 100 degrees, we obtained the formyl compound 9 in 72% yield. After accessing 9, we tried to set the stage towards the steel cross-coupling reaction we proposed initially. So we protected the free phenol as the trifluoride ester with N-phenyltrifimide and sodium hydride in 95% yield, and then protected the formyl group as dimethyl acetal with trimethyl orthoformate under camphor sulfonic acid catalysis in methanol. All these reactions performed very well. And then we ran a steel annihilation with allyl tributyltin and the palladium catalysis provided by bis-triphenylphosphine palladium dichloride. We also added lithium chloride because it is known that when you have triflates as starting materials, it improves the yields. And in order to avoid formation of palladium black, we added a small amount of triphenylphosphine, and after 18 hours of heating in DMF, we obtained 18% yield of compound 11. Once we got compound 11, we deprotected the acetal, and this took place during silica gel column chromatography. This was quantitative, we assumed, and with the compound in our hands, we performed a methoxymation reaction with a methoxylamine hydrochloride using sodium acetate as base in ethanol at 50 degrees. And in this way, we got 76% yield of compound 13. Now, all that was needed to get the natural product was a good cyclization. So we submitted our compound to an ASA-HEC reaction in the terms it was disclosed by Tsutsui in Narasaka and Narasaka in this 2001 paper with tetrakis, triethylamine in the presence of tetrabutylammonium chloride in DMF at 80 degrees. But surprisingly, we got only 18% yield of compound 1. So we were disappointed at this time. The yield was not satisfactory, so we devised a second alternative route, which included first a double bond isomerization with the same catalyst we used for our steel reaction, and we got this isomerized compound in 75% yield. We performed next the methoxymation under the same conditions as before, but here we got 85% yield of compound 15, and this compound 15 is a 1-ASA-3N, which we were able to electrocyclize when we submitted this compound to microwave heating to a temperature of 180 degrees for 30 minutes in 1,2-dichlorobenzene, and much to our satisfaction and happiness, we got 80% yield of compound 1. Well, great was our surprise when we compared the proton NMR spectrum of our synthetic compound 1 with that compound described by Proksch. This array of colors means to be a color map where the red means huge differences in chemical shifts. You can see here 0.52 ppm. You can see here 0.27 ppm. And green means minor differences, 0.01 ppm. So at this point, we were sure that aspergillitine was not such compound, and we first were unsure if our synthesis proceeded as we were expecting. We checked all the data, and we were then assured that the proton NMR data were that of this structure. So we concluded that PROX should have been wrong. We checked the literature, made some speculations, and then came up with this compound, TMC-120B, a known compound from the literature isolated from Aspergillus ustus and Aspergillus pseudodeflectus, which was also synthesized. So we compared the aspergillitine after PROX with the proton data, NMR data of the natural and the synthetic TMC-120B, and we observed that all the data were almost perfectly matching, mainly except for the signal of H5. Here we observed 738 and here 783. So we thought here that perhaps this was a typographic error made by the group of PROX when they prepared their paper, their manuscript. So in order to improve our assurance about the structure of PROX's aspergillitine and its identity with TMC-120B and not with synthetic aspergillitine, we ran a comparison taking carbon-13 NMR data. So this is aspergillitine after PROX, and this column is our aspergillitine, and you can see huge differences in carbon-13 NMR data as high as 16.7 ppm. So it's clear that PROX aspergillitine was not ours. When we compare the data of naturally occurring TMC-120B with the reassignment of PROX's data, we found that the highest difference was only 1.2 ppm. So there was a perfect match between PROX's aspergillitine and the structure of TMC-120B. So to summarize and conclude about this section, I would say that we have accomplished the first synthesis of the chemical structure originally assigned to aspergillitine, which is an alkaloid isolated from Aspergillus versicolor, in 11 steps and 15% overall yield. We also proved that the originally proposed structure for aspergillitine was wrong, and also demonstrated that the reported spectral data for the natural product were compatible with the structure of alkaloid TMC-120B, a natural product isolated from Aspergillus ustus and Aspergillus pseudodeflectus. We also demonstrated through chemical synthesis of the proposed structure of aspergillitine that we were able to solve a key question regarding the metabolic capacities of Aspergillus versicolor. Aspergillus versicolor does not have an extraordinary metabolic system capable of synthesizing 2,3-dimethyl-chromones. So we were enthusiastic about TMC-120B. So we said, well, why don't we synthesize TMC-120B? In this case, we felt a little bit short of making the total synthesis because our synthesis went too long. But I will tell you about our progress in the synthesis of key intermediate towards pseudodeflectusin and TMC 120B. To introduce the subject, I have to say that the naturally occurring 2-methylene 3-benzofuranone derivatives have many biological activities which are always interesting. They are anti-cancer agents and also anti-protozoan agents. So in the middle of the 90s, from Aspergillus ustus, the strain TC1118, the group of Komatsubara in Japan isolated this compound by the name TMC 120B. This compound was not isolated as a single compound alone, but it was also isolated along with other TMC 120 alkaloids and with this compound termed pseudodeflectusin, which was found to be an anti-cancer, have anti-cancer activity. It has anti-proliferative activity, actually. So our idea was to prepare an advanced intermediate towards TMC 120B with this skeleton, and we performed a retrosynthetic analysis as before. We've started disconnecting the ring C with the same reactions we used before, and this discovered for us intermediate A as a suitable advanced intermediate toward TMC 120B, which has here an R, which should be an halogen or an OH group, and a formyl group here. We advanced our analysis, made an oxidative fission here. We thought that could bring us the aldehyde, and so we thought that an allele moiety here would be a good precursor of this aldehyde, and we also thought that this methyl group would come from a Grignard addition to a carbonyl, followed by dehydration. And also, this ketone would be a result of oxidation of this alcohol. So we continued and simplified intermediate B and found intermediate C, a salicylaldehyde derivative, as a precursor, which seemed to be suitable. And in this case, we considered that having an OH here, we could easily install the allele group required for the aldehyde without any problem at the ortho position, and we can make this five-member ring through an O-alkylation of the phenol with this 3-carbon atom chain, and also using the position alpha to the carbonyl, perform a cross-aldol reaction with the aldehyde. So with that ideas in mind, we got compound C, and we further simplified C, thinking that ortho formulation of the phenol, for example, through the Kasnatis-Catewal procedure, would lead us to this commercially available phenol. To summarize this slide, our idea was to synthesize an advanced key intermediate toward TMC 120B from this phenol. For the first slide, for the next slide, I will show you on purpose, I omitted the formyl group here. So we started with the commercially available 3-bromophenol, this compound 1, and reacted this in the presence of paraformaldehyde, magnesium chloride, and triethylamine, conditions of the Kasnatis-Catewal reaction in THF, at 75 degrees for 10 hours, and we got compound 2 in 75% yield. Then, after checking the characteristic formyl signal by proton NMR spectroscopy, we went ahead and performed the O-alkylation of this free OH with chloroacetone, potassium carbonate as base in acetone at 30 degrees for 4 hours. And in this way, we obtained 82% yield of compound 3. We also characterized the compound when we found these 2 protons resonating as a singlet at 4.69 ppm. Our next reaction was the cyclization to the colors aldol reaction between this side chain and this formyl group. To do that, we found that our best alternative was an organocatalytic reaction with L-proline as organocatalyst. This is a natural amino acid, very inexpensive, to which 1 equivalent of water was added in DMF. And after 1.5 days at room temperature, we obtained 84% yield of compound 4, which we were able to characterize. This stereochemistry, this 1,2 syn stereochemistry, is a result of mechanistic considerations, and the mechanism of this reaction has been theoretically and practically elucidated. So, with this in our hand, the next step was to add the methyl grignard as we proposed initially, and we added the methyl grignard using big lime as the most suitable solvent for this. In the presence of a little bit of ether, we obtained 5 in 49% yield, and then with John's reagent in acetone at -30 degrees, in half an hour, we were able to obtain compound 6 in 70% yield. And the last reaction toward our first target was the hydration of this tertiary alcohol to make this alpha-beta unsaturated ketone system. And we did this with metanesulfonyl chloride and pyridine in dichloromethane at 40 degrees during 17 hours. This is a very, very slow and smooth reaction. When we reached this compound, we noticed that we were not satisfied by the outcome of this transformation. We thought that the free OH group was interfering in several ways. First of all, it was consuming 1 mole of Grignard reagent, and on the other side, the magnesium alkoxide was insolubilizing the compound, taking it away from reaction with the magnesium reagent. So we protected the free alcohol with DHP and camphor sulfonic acid in catalytic amounts to get the THP ether, tetrahydropyranyl ether, in 70% yield, and then perform the linear addition. So now we observe that the yields were improved, and we didn't need to add big lime, and also we were able to oxidize this position with John's reagent. John's reagent contains sulfuric acid, so THP ethers are very sensitive to mineral acids, and we were able to first deprotect and secondly oxidize the free secondary alcohol to compound 6. So in this way, we obtain compound 7 in 7 steps to the way of the THP ether in 14% yield, which represents over a 25% improvement over our original route of 6 steps and 11% yield. However, we were interested in adding here a formyl moiety. So in order to solve this problem, we performed again the caspase-catechol formulation, but as projected, we ran first an O-allylation of this free phenol with allyl bromide and potassium carbonate, obtaining 11 in 93% yield, and then we heated this compound at 180 degrees in 1,2-dichlorobenzene and obtained the glycine rearranged compound, 12 in 83% yield. Next, we perform a series of reactions similar to ones I have talked before, an O-alkylation with chloroacetone to obtain 13, cyclization under proline catalysis to get 14, and direct Grignard addition, which was not very successful, towards compound 17, or better, PHP ether protection to get 15 and 70% yield, and Grignard addition on the protected compound to get 77% yield of compound 16. Oxidation of the protected and the unprotected alcohol both took place in 60% yield, giving this compound 18 with depending allyl moiety, and running the dehydration on this compound provided 60% yield of this key compound 19. However, since we wanted to have here a 4-mil moiety, what we did was to perform a kind of Lemieux-Johnson oxidative fission, which we call exhaustive oxidative fission with osmium tetroxide and potassium periodate in a mixture of the butyl alcohol and the phosphate buffer of pH 7.25. So in this way, this allyl moiety undergoes a double oxidative fission. It gives an aldehyde, which enolizes itself in the reaction medium, and then it is cut again to yield the aldehyde. We also performed the dehydration of this compound. In the overall yield we obtained 25% yield of compound 21, the one I will show you next, from compound 18 to the intermediacy of this compound 20. So what's left? Because in this case, we got the final compound in 10 steps and 2.5 overall yield. So this overall yield is too low, especially because of these steps, and this hindered the further reactions we needed, because our synthesis would became non-competitive. So what was left? 4-mil group protection, still coupling and deprotection, alkene or double bond isomerization, methoxybation, and 6-pi electrocyclization towards TMC 120B. We didn't carry out all these reactions because getting the required amounts of 21 to finish the synthesis was very difficult, and also because we anticipated that our total synthesis would be non-competitive in terms of yields. This is one of the drawbacks of a natural product total synthesis. If you are the first one in totally synthesizing a natural product, no problem with the yields. No matter what you get your final compound, it will be fine. However, if you are not the first one, the yields matter, and the elegancy and the overall picture of the synthesis are important. So we left the synthesis uncompleted, and this is another phase, this is an ugly phase of total synthesis of natural products. The third target I will talk you about today is the first total synthesis of a benzofuranone, actually the only one benzofuranone isolated from Verbesina luxemburgi. Verbesina luxemburgi is a plant, you can see it in the background here, which grows in the state of Bahia in Brazil. And according to the best of my knowledge, this is the only place in the world where this Verbesina wetzelburgi has been found. And it has been studied phytochemically only once, and several natural products have been isolated from the extract of the plant, among them this benzofuranone. And the amounts of benzofuranone which were isolated from the plant were so tiny that the natural product chemists responsible for its isolation were not able to fully describe its carbon-13 NMR, and also it is unknown whether or not this is a racemic compound, this is a secondary alcohol after all, or if it is the R or the S enantiomer. So we started, as usual, our retrosynthetic analysis of benzofuranone 1, and we thought that this alcohol and this ketone, we can, if needed, functionally interconvert them, so each one can be an alcohol or a ketone, and in this way, we thought that compound 2 could be a good precursor of 1. Compound 2 has here an OH, and this expression OPG means that here we may have an alcohol or a ketone fully protected and suitably protected. So, as before, we thought that this methyl group can be disconnected to unveil a ketone, and also this carbon-carbon bond can be disconnected to unveil this system with an acetonyl ether and an orthoaldehyde. And also, we can further disconnect the ether, meaning that we will need to perform an O-alkylation, and here the formyl group can also be detached to leave this compound 5 as a suitable intermediate towards 1, or as a suitable starting material towards 1. However, there are no commercially available compounds which are identical to 5. However, 5 can be further simplified to 6, to the acetophenone 6, which is commercially available, and seem to be a good starting material. So from the synthetic point of view, we started with 6 and protected the carbonyl with ethylene glycol under cerium 3-flake catalysis, and using 3-isopropyl orthoformate as activating agents. The reaction was performed in hexanes at room temperature for 4 hours, and the yields were unbelievably good. Changing and using here trimethyl orthoformate drastically reduces the yields. So with compound 2 in our hands, we performed the Kasnatis-Kattevold formulation as usual, and we obtained 3 in 93% yield, and then ran the O-alkylation under Williamson conditions, potassium carbonate, acetone at 45 degrees for 2.5 hours, and got compound 4 in 98% yield. And then, when we ran the organocatalytic cyclization with proline, we obtained a mixture of compound 5 and minor amounts of compound 7. Compound 7 should result from the non-catalyzed reaction, and because it is immaterial for us, the stereochemistry of these two centers at positions 2 and 3 of the benzofuran ring, so we used the mixture of these compounds, which was obtained the most quantitative yield for the next reaction. So we carried on, and the mixture was treated with methyl magnesium iodide to perform the Grignard addition, and in this case, the addition performed very well. We didn't require THP protection. However, we were able to recover starting material from that process. And compound 8, resulting from this Grignard addition, was oxidized with PDC and methylene chloride at room temperature for 3 hours. And this gave us the ketone, and also, surprisingly, PVC performed the deprotection of this ketal. We were not expecting this because PVC is a rather neutral agent, and this kind of reaction are more readily found in oxidations with pyridinium chlorochromate. But well, we took advantage of this and went further to dehydrate compound 9 to get 10, as usual, with methanosulfonyl chloride in pyridine. And this reaction took 48 hours, very, very slow. And however, the yield was rewarding, 91%. And with 10 in our hands, all what was left was to selectively reduce this exocyclic carbonyl. We did this with sodium borohydride and limiting amount of isopropyl alcohol in THF at -60 degrees to acquire some degree of selectivity for 1 hour. The yield was not good, only 35% of racemic compound 1, and the balance were 2 other compounds, those resulting from reduction, 1,2 reduction, addition of hydride in the 1,2 fashion, so an alcohol, or the 1,4 addition, the conjugate addition of hydride to give another compound, which we will see just in a minute. So we ran the reaction and obtained this compound in 53% yield based on recovered starting material. According to the alpha, to the optical rotation, it is the minus compound, the level rotatory compound, and the chemical yield was actually half of this 53%, and this was accompanied by 11% yield of this compound, the stereochemistry of which at this center we didn't know at the first moment. So we were not very satisfied also with this yield and changed our vegetable, went to the grocery store and acquired celeriac and used the celeriac chops in the same phosphate buffer, and after 4 hours we obtained our minus compound 1 in 83% yield based on recovered starting material, and the chemical yield without taking into account the recovered starting material was very, very good, higher than 45%. And this was not accompanied by this compound -1. So in this slide, this is to show you that our compound -1 coming from the biotransformation by celeriac was only enantioenriched, not optically pure 100%, and this is known that celeriac doesn't give you 100% enantiomeric excess of the S alcohol. This is the S enantiomer. This one, this small one, is the R enantiomer. And we confirmed the identity of both peaks by making a co-injection of the racemic compound and the enantioenriched biotransformed compound. And regarding compound -11, what we did to propose that the structure, that the configuration at this C2 center was S, was to simulate the circular dichroism of the R and the S stereomers. And in black is the observed curve, and in red, the one calculated using the Gaussian package. And as you can see, there is a high degree of similarity between both curves. And in this way, we were able to propose that this was the structure of -11. So to summarize and conclude about this section, we can say that we have achieved in 8 steps and with 57% overall yield, the first total enantioselective synthesis of compound -1, which is the only 2-isopropylidene 2H benzofuranone isolated from the Brazilian plant Verbicilla luxemburgi. Actually, this compound 1 is the only benzofuranone isolated from any Verbicilla plants around the world. Early protection of the acetophenone carbonyl moiety enabled us to perform a successful Casnatis-Catebol orthoformulation and also the Grignard addition step. And timely deprotection and successful biotransformations mediated by carrot or celeriac chops differentiated between the endocyclic and the exocyclic carbonyls and allowed us to get 1. And finally, we think that this strategy would be useful for the synthesis of related and still unsynthesized natural products. The final set of syntheses I will talk about are the synthesis of the pterofilins 2 and 4, and also a new synthesis of gerberinol 1. And our constraint here will be that the synthesis of pterofilins and gerberinol will be performed and carried out from a common intermediate and using a key reaction under different conditions. So to present our cast, I would like to show you that these are the 5 known pterofilins. They have these 4 have a common tricyclic puro 3,2C coumarin skeleton, which is shared with other natural products such as this neotansine lactone isolated from Salvia mycorrhiza. The pterofilins, in turn, were isolated from a plant by the name of Echeverria pterophylla, which grows in South Africa and is popularly known there as rock ash. Pterofilin 3, which is structurally speaking slightly different, it has a 6-member ring here, has another natural product which is very, very similar, botioclinin, and botioclinin has here a CC double bond. So our interest was in pterofilins 2 and 4, which are very similar. Pterofilin 4 has a carbonyl here group, and pterofilin 2 has a terminal methylene group here. The other compound we were interested in was gerberinol 1, which is a dimer, can be regarded as a dimer of this 4-hydroxycoumarin, which has a methyl group on these positions and an H group here in the on the bridge. And gerberinol 1 is related to known compounds like dicumarol, which is a known anticoagulant agent, to 1-methylgerberinol, a natural product, to a compound where R1 is a phenyl group, and this compound has HIV integrase 2 inhibiting activity, and it's also related to this compound, which is an inhibitor of the protease 3CL of the coronavirus, which causes SARS. SARS was an epidemic of the Far East back a decade ago or so. Well, gerberinol is isolated from Gerbera lanuginosa, an Indian plant with this beautiful, with flowers like this beautiful one. The gerberinol one was synthesized 2 or 3 times before, but as I can advance you, in lower yields than in our case. So, well, regarding our retrosynthetic analysis, we started with pterofilin 2, the most complex compound, and thought that this methylene group can be disconnected to unveil pterofilin 4, which is compound 2, and we can go from pterofilin 4 to pterofilin 2 through a Wittig olefination, which is a known reaction. And as usual, we perceived this 5-member ring as the result of O-alkylation and of this position and aldolization with this formyl group as before. So after these disconnections, we unveiled this compound 3, which is highly reactive, we assumed, because this is a tricarbonyl compound. And we also went ahead and disconnected compound 3, thinking that this formyl group can be introduced from a precursor like 4, and that 4 can be made from 5 through an heterocyclization, and 5 can be disconnected at these 2 levels, these 2 carbon-carbon bonds, and here a Michael addition, and here an aldolization, an aldol reaction would give us this compound 5, and in thinking this way, we found here a 5-member diketon, which is this 1, 2, 4 pentanodione, and this 1, 2, 3, 4-member compound, which should have here an aldehyde function suitable for aldolization, was this one, crotonaldehyde. So we thought that crotonaldehyde and this pentanodione will be our best and most suitable starting materials for the synthesis of the pterofilins. But looking at compounds 3 and 4, we thought that compound 4 would be a good precursor of gerberinol. All we need was to prepare a compound like 8 and to perform a Michael addition on it. Well, this, in this way, is our common intermediate. So, well, how do we synthesize this compound 4? So we started with the aldehyde and the 2,4-diketon, and serendipitously we found that phenylbutane 1,4-diol in a low amount performed organocatalytic reaction, Michael addition, and we obtained this compound mainly through this route A. And also we observed that as a result of the reaction of 6 and 7, we were able to obtain through a route B direct carbonate addition and elimination, compound 10. Since compound 10 was not amenazed to us and did not hinder future reactions, we took the mixture and submitted the mixture to reaction with copper chloride in DMF. We added lithium chloride to improve the solubility of the copper 2 salt, and in 45% overall yield, we got our starting acetophenone 5. What happened here? First, there was a cross-aldol reaction to give this cyclohexanone, and then there was a tautomerization, a base-assisted tautomerization of this compound 1 toward the dienol 2, and then there was an alpha carbonyl chlorination by the copper 2 chloride, followed by dehydrochlorination, dehydrohalogenation, and aromatization, which resulted in compound 5. Compound 5 was successfully cyclized to the 4-hydroxycoumarine 4 in 79% yield, employing diethyl carbonate as the needed 1 carbon syntone, and potassium terbutoxide as base. And with compound 4 in our hands, we performed this cascadable formulation as before. And when the reaction was run at 80 degrees, we surprisingly obtained 75% yield of this compound, which we assumed came from dehydration of this alcohol. And what would make dehydration of this compound became feasible? The high temperature. When we reduced the temperature to 50 degrees, this reaction leading to intermediate 3, which is a very good Michael acceptor and an intermediate of compound 8, instead of running this process, this was suppressed, and we got aldehyde 8, aldehyde 3 in 87% yield. From 2 to 3, the reaction, the key reaction in the middle, is a hydride transfer, is a kind of dehydrogenation, and in old times, this was called an open-hour oxidation reaction. In the classical open-hour oxidation reaction, which is catalyzed mainly by aluminum salts, it is used an aldehyde in excess, and this aldehyde is sacrificial because it is reduced to an alcohol. In this case, formaldehyde was reduced to methanol, and our substrate, our alcoholic substrate, is oxidized or dehydrogenated to the aldehyde. So we got 3 in 87% yield, and then we performed our known reactions. First was the reaction with chloroacetone to perform the O-alkylation, and we discovered that using Brockman 1 type basic alumina, we were able to perform the O-alkylation, the aldolization, and the dehydration all in one step and in 88% overall yield. To do this, we were inspired in this paper on Journal of Chemical Research of 1998. So in this way, we got pterofilin 4 in good yield, and then we performed the required methylation with this VT reagent, methylphenylphosphonium iodide, using potassium terbutoxide as a base. So we obtained pterofilin 2 in 58% yield and 78% yield based on the recovery of starting material. So to summarize this part of my talk, I would say that we have used a temperature-dependent Kasnatis-Catebol reaction to access either herberinol 1 at high temperature, 80 degrees, or to access the pterofilins 2 and 4, and all of them from a common intermediate. In this way, we accomplish the total synthesis of herberinol 1 in 4 steps and 29% overall yield, the synthesis of pterofilin 4 in 5 steps and 30% global yield, and the synthesis of pterofilin 2 in only 6 steps and 17% overall or general yield. And we performed all these syntheses without using any protecting group and without using heavy metal catalysis or catalysis by endangered metals. During the synthesis, we described the first use of the Kasnatis-Catebol reaction for the functionalization of C3 in 4-hydroxycoumarins. As you will see in one of the next slides, this was key for our next development. After synthesizing the pterofilins, one paper caught our attention. In this paper, this European Journal of Medicinal Chemistry of year 2016, it was described that ostol analogs, ostol is a natural product, are able to inhibit certain post-harvest phytopathogenic fungi. The authors of this paper prepared all these compounds, and they found that some of them were good inhibitors of these fungi. And why this problem is relevant? Well, because post-harvest phytopathogenic fungi are able to cause every year millions of dollars, reais or pesos in fruit losses. The use of natural products and their derivatives as a way to control these fungi is an acceptable structure. So we thought, well, why not to test our pterofilin 4, which is very similar to this compound, which has R1, a side chain similar to ours. It has a methyl group here, and it has an H here. So the methyl group in the compound, instead of being here, it is here in the ostol derivative. In order to do that, we selected 3 strains of different phytopathogenic fungi: Rhizopus solonifer, Molinilia fructicola, and Botrytis cinerea, which are responsible of the black, brown, and gray mold rods. And in order to make more interesting the problem, we prepared a small library of compounds. So we synthesized an analog of our pterofilins, starting from this commercially available acetophenone compound. We first prepared the 4-hydroxycoumarin and then performed the O-alkylation. When we tried to do the Vilsmeier-Hack formulation, this didn't work. So instead, we went back and ran our known Kasnatis-Catebol formulation, and this gave us a very good yield of compound 3, the 3-formyl derivative. And because we thought the formyl derivative will be highly reactive, we protected it as an imine with this amino alcohol in hot toluene in 75% yield. And then we tried to perform the O-alkylation of this compound. However, we not only succeeded with the O-alkylation, but also the reaction went further, and we ended up with compound 6, our final product. However, we were not satisfied with the yield. The yield was very, very low. So we have no other alternative but to use our Brockman 1 alumina to do this two-step reaction, and in this way we obtain compound 6 also in 88% yield. So to sum up, we were able to prepare 8 analogs, which are listed here with different numbers than before, from 1 to 8. The first 2 are our pterofilins, 2 and 4. The third compound number 3 is an analog of the pterofilins lacking the methyl group here. And then we have different bicyclic coumarin derivatives. And as you can see, when we run the test, MIC means the minimum inhibitory concentration, and MFC is the minimum fungicidal concentration. We observe that compounds 4, 5, and 6 were fully inactive. Our compounds exhibit mild activity, and the best results were those of compound 2, our pterofilin 4, against Molinilia fructicola. In order to validate our tests, imazalil and carbendazim, which are known antifungal agents, were used as positive control comparators. This slide is just to show you the macroscopic side of how you can see the treated samples, the compound treated, the fungi treated with pterofilin 4. These 4 Petri plates are our control plates without the addition of pterofilin 4. You can see this Petri plate with Rhizopus solonifer at 38 hours, and at 43 hours, there is a big change here. This is the microscopic observation of the treated and the control colonies, and you see that there is much less development, fungal development, in the treated than in the control samples. And we took a small sample of treated and controls and stained it with lactophenol blue. Unfortunately, my best picture is a black and white one, but you can see here sporangia, which are body fruits of the fungi or pre-body fruit. And here you see that the development of the hyphae are like the branches of the fungi, and they are thinner than in the control. So you can see that pterofilin is somehow slowing the growth of the fungi or inhibiting the growth. So to conclude about this section, we prepared a small library including 8 compounds, among them the pterofilins 2, 4, and their intermediate analogs. The compounds were tested against a panel of 3 selected post-harvest fruit phytopathogen fungi, meaning Rhizopus solonifer, Molinilia fructicola, and Botrytis cinerea. Pterofilin 4, as observed, displayed weak activity against Molinilia fructicola. And as a result of these observations, we can also conclude or suggest that the pterofilins may be acting as plant defense agent, because if the compound is active against one fungus, it is probably active against other fungi. Well, to finish my talk, I would like to thank the financial support my group has been receiving from our National Research Council, the name is CONICET, our National Agency for the Promotion of Science and Technology, AMSIT, which we know familiarly as the agency, and from the Secretary of Science and Technology of our university, which give us very, very little amount of money, but it's money after all. And we will also like to thank my research group. This is a changing group, a group which changes upon time. These 4 students have been working in my group before the pandemics broke, and this student is supposed to keep working with us after the pandemics. This lady is currently working with us a couple of days a week, despite the pandemic. This is Dr. Braca, Andrea Braca, one of my right hands in the laboratory, and here in the back is Dr. Enrique Largui. As I told you, perhaps today, Enrique did his PhD and master's student studies at the Federal University of Santa Maria. And well, this is Sebastián Simonetti. He performed all the synthesis of aspergillitine, all this work. And this lady is Jorgelina Pergomet. He did all the rest of the work. And Jorgelina is currently in Germany. She is working in a chemical plant. I would also like to tell you that this is the external view of the building, the new building of my institute. We have only built two floors, one underground and this one, and the remaining 50% of the building is a big loft, and hopefully, if sometime it is finished, I will probably have an office here and a lab perhaps here. So, well, I thank you very much. This is an aerial view of my city, Rosario. Thank you very much for your attention, and I will stop sharing my screen and will be open to questions.
Okay, Professor Teodoro. Once again, thank you very much for the presentation, the excellent lecture for accepting the lecture. I have some questions. Questions is for Fabiani. Has the biological activity of these molecules been tested? And if so, is the result close to the natural molecules when compared to the synthetic ones?
Pterofilins. Regarding aspergillitine, we have not tested yet its biological activity because aspergillitine is not a natural product. Because it's not a natural product, unless it has a high and unusual biological activity, it has no interest to test the biological activity of a single isolated compound. PMC 120B, it is known that it has anti-cancer activity. And regarding the natural product found in Verbesina luxemburgi, we have not tested the activity. The pterofilins have not been tested before our experiments. So the people who isolated the pterofilins have not tested its activity. And to the best of my knowledge, gerberinol has not been tested either. However, there is a strong belief that coumarins are associated with anticoagulant activity. The lady who synthesized gerberinol, she left our group, and we have only milligrams of gerberinol, and we never set up experiments nor collaborations to test its activity. Hope I have fully answered the question, and if there is something left, please remind me what's left.
Okay. No more questions? You finish, Cesar?
Okay.
Okay, Professor Kaufman, your screen is still being shared with us. If you can stop it.
Yes, sure.
We thank you very much.
Okay, I have stopped sharing my screen.
Okay, Professor, now just let me thank you very much for your time, for your kind presentation, and for accepting our invitation. It's a very nice pleasure to have you here. As I already talked with you, please feel yourself welcome to be here in Santa Maria with us as soon as it's possible, considering the pandemic restrictions that we are now living at this moment. Okay, now just let me speak in Portuguese because I have some knowledge to do now for people that are using to help me in these transmissions. Ok. Então, eu agradeci ao professor Kaufman, né, o professor Teodoro Kaufman, palestra realmente bastante interessante, e eu acho que essa é a proposta que nós temos aqui, né, no programa, convidar pessoas que tenham expertise, pessoas que tenham bagagem, para que possam apresentar os seus trabalhos, e esses trabalhos possam, digamos assim, contribuir para a formação dos nossos alunos, para que a gente continue formando recursos humanos qualificados, aptos a ingressarem no mercado de trabalho, né, e darem a sua contribuição com o social. Então, essa é a nossa expectativa, e eu acho que o professor Kaufman certamente colaborou neste aspecto. Eu gostaria de fazer alguns agradecimentos. Hoje nós tivemos uma surpresa antes da apresentação, né, quando a gente foi testar o computador, ele estava dando uma mensagem de HD queimado, né, o que comprometeria um pouco a nossa transmissão aqui. Então, eu gostaria de agradecer ao Henrique do CCNE, que prontamente se disponibilizou a nos emprestar uma máquina. Ela não foi necessária, né, o computador não foi necessário, mas, enfim, nos emprestou e a gente teve essa alternativa. Como sempre, eu gostaria de agradecer a Vitória, né, que é a nossa representante discente e a pessoa responsável pelo streaming, né, que faz a comunicação entre a sala do Google Meet e o YouTube, né, sem a qual ficaria bastante difícil uma única pessoa fazer toda essa, digamos assim, comunicação, né? E, finalmente, eu gostaria de agradecer a todas as pessoas que prestigiaram e todas as pessoas que virão a prestigiar, uma vez que essa palestra ficará disponível no YouTube. Então, a vocês que prestigiaram, os nossos agradecimentos, espero que possamos contar com vocês em próximas ocasiões. Professor Kaufman, professor Bernardo, muito obrigado pela presença de vocês, né? Nos vemos numa próxima oportunidade. Um abraço.
Agradecido soy yo. Muy, pero muy amable.
Bueno, gracias.
Muchas gracias, Bernardo. Muchas gracias a você. Y seguimos en contacto. Adiós.
Pronto, adiós.